Hi everybody, I'm Krishna. Okay, so yeah, that's my topic, quantum computing. We'll call it QC, okay? And CC is classical computing. Okay, so yeah, before starting, anybody knows what a quantum world is? It's not hypothetical, okay? It's real. It was theoretical, but now it's real. Okay, so yeah, I was asking if anybody knows what a quantum world is. Raise hands, just any assumptions. If you have any idea what a quantum world is. Yeah. Yeah, correct. Hmm. Yeah, it's yeah, it's a superposition thing. We'll discuss about it in further in lecture. Okay. So yeah, let's start from the basics. Okay. Before that, I will just introduce myself. Okay, I'm Krishna Thite. I work as a private contractor with government agencies. I was cybersecurity engineer. Then I just focused on forensics, and right now I'm just researching on quantum computing from last 6 months. And I guess this is the first time I'm presenting quantum computing in front of audience. Okay, so if you have any questions in physics, we'll discuss that later. But if you have any questions related to quantum mechanics and quantum computing, we'll discuss it right now. Any questions, okay? Even silly questions are allowed. So quantum computing is CC, QC, and classical computing is CC. Classical computing means our regular computers or supercomputers, okay? So this is the agenda: classical computing and quantum computing. How does the quantum computer work? Quantum computers impact on cybersecurity. Store now, decrypt later. Is this the big idea? Okay, we know that AI was a big idea in 2018 and 17, and now it's hitting us. Quantum computing is the next big idea, which will be hitting in next 10 to 15 years, approximate. Okay. Before that, I will just read something. Okay. Does anybody know about Richard Feynman? Raise hand, just if you know him. Sir Richard Feynman. One, two, three, four, five. Richard Feynman. Just this face. It's made with AI, but okay. Richard Feynman. I will just introduce him. So he was a guy who is known as a father of nanotechnology. Okay, and he was the father of quantum computing. So what he says is, you can just read. I will also read. Okay. Trying to find a computer simulation of physics seems to me to be an accident to follow out. The real use of it would be with quantum mechanics. Nature isn't classical, and if you want to make a simulation of nature, you would better make it quantum mechanical. By golly of its wonderful problem, because it doesn't look so easy. Complex, right? Even I don't understand what he says, but yeah. Uh, so let's go back. Okay, can you see here? This is so here. Schrodinger was a scientist. Basically, he proposed a theory of, you can say, probability. Okay, I will just explain it in a layman term. Imagine a box. Okay, a box and a cat inside it, and a device which may kill it. Okay, how many of you know about this? One, two, three, four, five, six. Okay, anybody want to explain it? Nobody. It's complex, right? Okay. Oh, you.
So basic was that Schrodinger suggested that there is a box inside it. There is a cat, but you are not sure if there is a cat or not until you open it. So it's like it can have anything out of it. It can have the cat or it cannot have the cat, and until you don't open it, you can't be sure. So that's what gives the idea basically.
So yeah, little bit here there, but quantum computing, quantum mechanics is probabilistic in nature, and it's not deterministic. Okay, so I will explain the experiment. Okay, so there is a cat. inside a box, and there's a device which may kill it. So the box is closed. Now there is a 50-50 possibility that the cat is alive or dead. But the second before you open that box, the cat is half alive, half dead. That proposed the theory of superposition in quantum computer. Okay, I'm seeing a lot of confused faces here, but just know that a regular computer works in binary, right? Everybody agrees, 1 or 0. And in quantum computer, we have superposition, which is 0 and 1 at the same time. Just like the cat is alive and dead at the same time. So this was a theory, and after that, Sir Richard Feynman came and just made some theorems, algorithms, and he wanted to simulate subatomic particles. And the computer he had wasn't, capable enough to, just simulate the particles. So he just made an idea, not a real computer, just had a mathematical equation and formulas. And yeah, he proposed the theory of quantum computer, and right now we have Intel, Google, IBM, Atom fighting for quantum supremacy. Okay, so what was necessity of quantum computer? Okay, so there is a Morse law. Okay, this is more of a physics lecture, I think. Okay, so understand that there is a Morse law. What Morse law says is, Morse law is nothing but of observation that number of transistor in a dense integrated circuit doubles every 2 years, correct? Okay, so our chipsets are going small, 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 and at any time it will hit the limit. Okay, उसके उससे नीचे हम बना नहीं सकते उससे छोटा. Okay, so what Richard Feynman did is he went into the bottom of the world, which is known as quantum world. He says that there is plenty of room at the bottom. Okay, so uh, the particles at the subatomic level behave nothing like at larger scale. So let's think about it. How quantum computer and right now we have a computers, how they differ. Before that, sorry, mechanics, quantum mechanics, physics. Okay, yeah. Right now everybody is on the same page. Just know that it's a uh, Richard Feynman says that you're not going to understand it. You see, my physics students don't even understand this because I don't understand it. Quantum electrodynamics, the theory of quantum electrodynamics is absurd in nature, and it's totally experimental. But you have to accept nature as it is absurd. Okay. So yeah, before we know about quantum, and so we'll know about quantum and classical. So everybody had science in the 11th and 12th, right? Physics, Sir Isaac Newton, mass is equal to force is equal to mass into acceleration, correct? So classical mechanics works in this world, fan, this thing. I just need a pen. Do you have a pen? Just thank you. So imagine, so don't imagine, this is a pen. Okay. So yeah, classical mechanics says that you can predict the future of this pen 100%. Okay, if you know the initial information of this pen. Okay, you know the mass, the speed and all. And if I throw the pen from here, it will exactly land there, 100%. But quantum mechanics is totally different. Okay, thank you. So, as I said, quantum mechanics is probabilistic and non-deterministic in nature. So, as we read here, yeah, the thing is, it is totally governed by Schrodinger's theory. Okay, because of that, 0 and 1, we have superposition right now. Yeah, energy changes in discrete step called quantas. Okay, particles behave as both waves and particles. Yeah, that's really interesting. So you might have known about the waves. They travel like this, and there are particles. Okay, at quantum stage, they behave as particle and wave at the same time. Okay, yeah, that's the principle. Even I don't understand how. That's nature. Absurd. The thing is, uh, when we see that electrons or photons or ions, they have their own behavior at their world. We have our behavior in this world. We behave according to our behavior. Okay, they behave. Electron doesn't orbit around the nucleus like this. Planets revolve around the sun, correct? The electrons orbit in a fuzzy situation. We cannot predict it. It's somewhere, but we don't know where it is, and we cannot even predict it. ये कहाँ जाएगा ये? Okay, because of that we have quantum uncertainty, Heisenberg's theory. um, yeah, yeah, this is this is the do you understand anything? I don't understand, but yeah. So this is quantum equation. Okay, anybody wants to explain it? इससे साइबर सिक्योरिटी का क्या लेने देना? हम फिजिक्स की क्लास में आए हैं. Anybody? This brainstorm. मुझे लग रहा है बहुत फिजिक्स में जा रहे हैं हम. We'll come back. Okay. As I said, nobody understands quantum mechanics. Okay. Okay. Don't worry if you don't understand it. Even I don't understand it. Okay. Because that's absurd, dude. Just keep in mind that. Okay. Yeah. Okay. Now you will understand what is happening. Can you observe it? That's a classical bit which is used in our computer, and that's a qubit. Qubit means the bits used in a quantum computer. Can you see that the charge here is it is spinning and horizontally vertically at the same time. So we can just say that this is 0 vertically, sorry, horizontally when it revolves, and when it revolves vertically it's 1. Okay, so as I said, we don't know where the electron will be or how it's spinning. He acts as he's the king of that world. So yeah, because of that we have quantum bit, and we use his that energy to calculate. Okay, we'll discuss about it. How do we compute with a qubit? How do we manipulate it to solve our problems? Till here मैं ज़्यादा fast जा रहा हूँ. Okay. Okay. Yeah. So yeah, uh, classical computer work on voltage, circuit, gates. Okay, and our quantum computer works with superposition, entanglement, and decoherence. Okay, uh, leave entanglement and decoherence right now. We'll focus on superposition. Okay, keep in mind superposition is nothing but 1 and 0 at the same time, and it gives acceleration to computation. Again, okay, so this is nothing but the quantum state. This is a symbol for quantum state. Okay, it may look like a psychology symbol, but it's a quantum state. Okay, so we'll understand quantum computer with a flow chart. Okay, so we have a preparation here. So this is the initial stage of quantum computer. Okay, it's a quantum state here. Then what happens is we come to the second part where evolution take place. Okay, it changes using unitary transformation. So what is unitary transformation? Unitary transformation is like it is a mathematical operation that changes the state of quantum system in a way that it doesn't lose any information. Okay, that's unitary transformation. And here we have steps like it is going from T1 to T0, T2, T1, and Tn and Tn minus 1. These are the steps. Okay, and at the end we have measurement. So imagine that at the end it collapses. अगर हमने imagine that cat का box था, we opened it and we found that cat was dead. At the end we measure it. Okay, we found that cat was dead, and at the end we measure the probability of quantum qubit with this formula. Okay, either it will be 1 or 0. What is it? Okay, I think I'm going a little fast here. Okay, if you have any question, just ask. क्योंकि मैं आगे चले जाऊंगा फिर तुम्हें समझ नहीं आएगा. Any questions? We can just repeat it. Yeah, so it was theoretical. Many people think that quantum computing is a theory, but we have quantum computers right now running. Even on, if you go on IBM's website, you can access quantum computer through Qiskit. Qiskit is a program. Okay, from that you can actually access a quantum computer for your educational purpose or anything. Okay, so it's not theoretical totally right now. It is real. Like AI was theoretical, now it's real. Likewise. Any other question?
Why I asked that was in one of the session, we were talking about AI and what will be the future will be the quantum this computer in the space of cybersecurity. So when that opens up, when now the AI that itself is not stable as of now. So as of now, the AI itself is not stable. As of now, I myself am a cybersecurity manager. Okay, in my organization, just to even translate our normal usage of the AI, we had to give a lot many direction to the people for the responsible usage of AI. Okay, and then also people are not understanding the impact of it, how negatively and positively it will impact. It's like the two side of the coins, the cybersecurity for AI and AI in cybersecurity. Okay, so how I mean one of the point which was 80%, once the entire data will be used, then also it will be 80% only, the 80% of the usability and the accuracy of the AI. Okay, then also it will not be 100%. So when we are talking about the security, that is like the Six Sigma, what we say 99.9999, that kind of quality we want in that space. When we are talking about the cyber security and we are saying broadly that we will be using AI in cyber security, quantum computing is a totally different ball game. So that's why I was asking how impactful it is as of now. That was the question. Yeah.
So yes, as far as you know, so imagine it as quantum. So AI as a human. So there is a debate that AI will have consciousness or not. Okay, but imagine it has a consciousness, and quantum computing is a nuclear weapon for that human. And if we integrate AI with cybersecurity, right now we have use cases of AI. So in general, quantum computer are useless. Okay, they're useless. But the limited usage it has makes the basics of cryptography and biotechnology. We'll not speak about biotechnology right now, cryptography. Okay, and you know that cryptography is the basics of cybersecurity. Every inscription we will be learning about ECC and RSA, how to break them with quantum computer and how it actually breaks them. Okay, so that does that give you an idea of will it do that or don't? Even I'm not sure that it will do or not. Hmm. 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 Accurate. Accurate. Yeah, so you're talking about the accuracy of quantum computing, the result. Hmm. Yeah, as we know that computers don't do mistake. Same goes for quantum computer. As we discussed right now, quantum computer is not a computer, it's a technology. It doesn't work on a processor, Intel processor M1 किसी पे काम नहीं करता. It works on a subatomic level where we isolate the particles like electrons, ions and photons and make them behave in a way that we can compute our calculations. That's the thing. Okay, so if you talk about future, I cannot predict it. It's a double-edged sword. So we can just right now we are, AI has come and we are in the middle of that. That if AI comes in a full power, what will do? So even I don't know what we'll do when quantum computer comes in full power. But right now, the qubit it has is maximum. Right now we have 1,000 qubits of, you know, the biggest one is of 1,000 qubit from atom. Okay, and the big giants like Google and IBM have 156, 300, 200 qubits of quantum computer. So it's really far to be a nuclear weapon. So kind of a nuclear weapon, but we can really use quantum computer in next 10 years. But it will be a lethal weapon. We are not sure for next 2 to 20 to 30 years. That's my prediction. Okay. Yeah. So yeah, this is the circuit. We are getting on the same point from different approaches. Okay. How does a quantum computer work? Okay. So imagine this as these are quantum states, right? Imagine them as wires carrying qubits. Qubits are going through them. Okay. And this is the end where the measurement takes place. The measurement collapses. We'll get 0 or 1. Okay. So uh, let's see that applies. This operation preserves the total probability. Same as flowchart. Okay. Same, literally the same, but from a different approach. Here, just we have used qubits. As I said, we manipulate here, nothing else. We manipulate qubit here to perform calculations, nothing else. That I just discussed right now. Uh, Like this. This is not a screen, not a nothing, but this is a quantum computer. It looks like this and works like this. Okay. So before we go here, okay. So yeah, this is just a quantum computer. We isolate the electron inside this, okay, to make the calculation and get our results here. I don't know if you can see there are zeros and ones here. Okay, no worry. Okay, so last thing we'll discuss about quantum computer and then we'll move to cybersecurity. Okay, so exactly how does it work? So we'll use, there are number of particles in our world, in subatomic world, like ions, photons, molecule, any atom, atom. Okay, we'll use electron as atom. Okay, so yeah, so when we use electron as atom, we electron as qubit. Okay, so it behaves in his own way. It doesn't revolve like planets around sun. Okay, uh, and then we have initializing the qubit. So yeah, as I said, in the quantum computer we isolate the electron in a chamber. So for that, the room temperature we have right now, the particles behave in a very fast manner, so we cannot control them. So we have to take them to a low temperature so that we can control their behavior. Then we have unitary transformation. There is one unique feature of unitary transformation, that it doesn't lose information, it just rearranges it so that we can reverse the operation anytime, any given day. That is the unique feature of quantum computer running an algorithm. So it's basically running an algorithm. We can just Shaw's algorithm, Grover's algorithm. Then we have every other algorithm working with quantum computer has different results. Okay, so Shaw's algorithm is used to break RSA. Grover's algorithm is used to break brute force attack. We can do brute force attack from that. And there are lots of algorithms. And measurement, as I said, at the end. And remember that we at the end we have a classical bit. It is measured in a classical bit, not a qubit. Okay, even it's a quantum computer, at the end we will have 0 or 1, correct? So it will be measured as 0 or 1 binary language, a classical bit. Okay, this is how this is both sphere. Actually, this is the visual representation of a qubit. It's not a circle, it's a sphere. Okay, and these are the, this is how we trap the electron in a quantum computer. So superconductor loops, trapped ions, topological qubits, silicon quantum dots. Okay, we trap the electron in a quantum computer through magnetic field or quantum dots, which is a man-made superconductor. Okay, you have any doubt? Okay, anybody?
Currently the data flows in zeros and ones, so going forward when it comes to quantum computing, it would be in qubit, or are we going to use this qubit like to represent zeros and one in computer language? Because I think all the programming language and everything needs to be changed to, or like they would. Yes.
Is that going?
So you are saying that are we going to be in superposition for an entire time? Like zero will be in a definite position. Okay, either zero or other one. Quantum computing is just a operation where time is reduced and it accelerates the operation computation basically. Okay, so we'll be doing zeros and ones only. Yeah.
So like are qubits replacement for transistors?
Yeah, we can say that. Okay, because transistors, a transistor consists of a silicon plate, a drain, a source, and something is there on that thing. I don't remember it, but yeah, that controls the. You have the answer. Okay, so that controls the flow between source and drain. Okay, and there is a silicon plate. So take for example transistor. So circuit of 7 atoms. Okay, take example for that. Just imagine that, and I don't think so. You will be able to imagine. Okay, it's very complicated. Okay, okay, leave it. We are going more into physics right now. Okay, we'll come to cybersecurity. Sorry. Yeah, it's too complex. I know. Yeah, we'll discuss outside if you have any physics question because it it is everything about physics. Okay, but the thing is, we want is the use case, right? We are cybersecurity engineers and enthusiasts. We don't need this, but we'll discuss about use cases right now. Physics, when you talk about physics, we go to the basics. Okay, computation, we will be doing data analysis and all that with computers, but their physics won't apply. Okay, they're simple math. Okay, algorithms and maths, simple. Hardware, we can say CPU level. Okay, go beyond that. Okay, it's a theory, and when we make a hardware out of that, then we do the analysis, then we do data analysis and all that. Okay, it's just the basics, the a skeleton of a approach. So don't think that we'll be using qubits as whole in our future, because quantum computer we won't be able to handle it right now, general public. If you say only the governments and the big giants are doing that for large data processing. Okay, we came to breaking huh, impact on our side of the game, cybersecurity. Okay, so when we think about it, it's useless for general tasks. Okay, so but the very basics, so very limited tasks it has makes the basics of cryptography. So breaking classical encryptions, and yeah, we have to think from other side too, that we have to make a quantum resistant world. Okay, we'll discuss about that. Mm, RSA and ECC. Everybody knows about RSA used in banking, e-commerce. Okay, yeah. So yeah, and so imagine, so basically RSA works like with public and private key, right? So when we have, so take for example, uh, public key as n. Okay, n becomes, so I'm just going in maths right now. So take n. Okay, n becomes a part of public key. Now, without private key you cannot decrypt the message, right? You have the public key. Public key is open for everybody, but you don't have the private key. So take for example n, which becomes the part of public key. Then we have p and q. Oh, I just go back. Okay, factor. So RSA works on factorization. Everybody knows that. Okay, so take a big number. The basic principle of RSA is to factorize the big prime number, not of 10, 5, 6 digit, about hundreds of digit. Okay, so if you make the factorization of prime number, so we get two other prime numbers, right? Take 4. The factors are 2 and 2, correct? So yeah, RSA works on this. Okay, but the thing is, classical computers are not capable enough to make the factors of that particular big number. So that's why we have quantum computer right now. So quantum computer are capable enough to make factors of a big number. So yeah, RSA works on that. We know that RSA works. So come right now in the present where we talked about N is the public key. Okay. So we need P and Q, which are the factors of N. Okay. So the formula goes like to take a private to know the private key, we need to do P minus 1 into Q minus 1. Okay. So we don't know the private key until and unless we don't do the maths. Okay. And our classical computers are not capable enough to do that. So yeah, quantum computer will do that. ECC, elliptic curve cryptography, it looks like this. Okay. Again, we are just, this is an encryption. Okay, just like RSA, but instead of working on factorization of prime numbers, it works on geometry. So it solves the elliptic curve, uh, uh, what it is, logarithmic problem, EDLP. Okay, it solves that and makes encryption. So again, same principle that we have a larger computer, quantum computer, it can solve that. Okay, I'm just running fast because I have 10 minutes left, right? Volunteers, yes, asleep. How much time do I have? 5 minutes. Okay. Okay, Grover's algorithm. It's a big PPT. Okay. Sorry for that. But we'll come to post quantum cryptography. NIST is working on that. So the thing is, when quantum computer comes, we don't have, we don't have protection against cryptography. You think that, okay? But the thing is, even quantum computer are not able to break the encryption from SHA-256 because it has 256 keys, right? It can break AES 128, any encryption that uses 128 keys. Okay, so that it can break. So for that we have to make a quantum resistant world. So there are two approaches: either make the 128 bits of keys to 56, or just do something that will just block the quantum computer access. Okay, so if we have AES 128, make that AES 256, but sometimes it's impossible to do that with maths. Okay, yeah, we have certain methods we can use for quantum resistant cryptography, lattice based cryptography. So basically there are lattice, anybody know what is lattice is? Those are just dots on a plane in a square. So we use that. I don't know if I have time to just explain that. We have code based cryptography, just error correcting. We are doing that right now with artificial intelligence, right? We are just correcting our code again and again and again with artificial intelligence. Then we have a hash based signature. Using hash function, we can make a hash signature. Okay. Then we have multivariate cryptography, that again goes in polynomial equations and all, more mathematics. Yeah, last topic we'll cover it, QKD. Now this is theoretical, okay, but I want to explain it because QKD works on photons. What are photons? The light particles, even the light bulb. So it's a tube. So there are particles in that, right? Those are flowing. So we use that particles to encrypt the message like this. This is the photon. Okay, those are the two gates. Okay, in quantum world we have gates: X gate, Y gate, H gate, which are used to manipulate the photon, and get 1 or 0 at the end. But the thing is, what we do here is we encrypt the message here. So as we can see, 1 0 1 1 0 0 1 0 0 1 1 1 0. Okay, when it goes horizontally and vertically, it gives us 1. When it goes diagonally, it gives us 0. Okay, same, we use that technique to encrypt the message. So it's impossible for someone to predict the behavior of a photon. Okay, as I said, we cannot predict it. Even hacker cannot predict it. Even if he did, it will be useless for him because QKD again detects the intrusion. If we intrude, the Alice and Bob will never use that private key again. Okay, this is again the same. Quantum cryptanalysis is nothing but using simulating quantum attacks right now. So last topic is that even quantum computer is not here yet. It's a problem. How? So there are big giants like government agencies and other people are just storing the information of opposite nation. The you know that the credit cards and password are not stored in plain text in the server, correct? They're stored in hash encrypted form. So they are storing it right now so that they can decrypt it later with quantum computer. People won't change the password if quantum computer comes, will they? So when it comes, they will decrypt it. So that is known as uh, yeah, store now, decrypt later. It's a threat right now. Yeah, just I said that we'll use instead of AES 128, we'll use AES 256 to be quantum resistant. Just going back. Yeah, just imagine now, will if we just integrated AI and quantum computer. As I said, it will be a lethal weapon if we integrated that two things. This I wanted to explain this, but yeah, you can just people are just clicking the photos. Okay, yeah, these are some companies fighting for quantum supremacy: Toshiba, Google, NEC, KPN, Microsoft. These are some startups there, hardware and software. People working on software, people working on hardware. If you want to click any pictures or anything. Done? Yeah, I wanted to show a demo, but this is the code I have used through Qiskit. Qiskit is it's a free platform for everybody. You can just type this code, and here I have used the public number. Public. So yeah, it has just done the factorization through source algorithm. Okay, we can just go in from Python program. You can just download Qiskit and just import the libraries here. AER, quantum circuit, transpile, assembly, and execute. Other libraries. Done. Yeah, I have this algorithm is used to break RSA. We can literally break RSA through this. We have just imported the quantum computer from Qiskit. That's it. Nothing else. Does that? There minutes, minutes, 2 minutes, 200 seconds specifically. If I were to say, depends on the number. How big is the number? If it's 200 digit, the maximum number a classical computer can handle is 216 of number of digit. Okay, beyond that it cannot, but quantum computer can. Qiskit, yeah, IBM is using quantum computer. They have, yeah, IBM's product. And this is a GitHub repository. If you don't want to code, you just go there and just type your message. It will decrypt it. Again, this is for educational purposes. Yeah, it's available on GitHub. There is only one repository for this. I wanted to show you one research paper, but I guess the time is up. Okay. I guess you have the introduction for quantum computing. Okay. Was it good? Yeah. Thank you.